In this video, we're going to start off with section 5.3, associations in categorical variables. And we're mainly going to focus this section on finding conditional probabilities. So let's first start off by talking about associations between categorical variables. So for a quick second, I want to focus on this word association. In last chapter, recall, in chapter 4, right, we talked about associations a lot. We focused on bivariate numerical data sets, and we were trying to find if one or the other had an association. So, right, like does CO2 depend on the year? Does CO2 depend on temperature, right? We're trying to find an association. So kind of similar to what we're going to do right now. This table shows marital status and education level for a random sample. So we have two variables, except we're talking about categorical, right? Marital status and education level. And the question is there an association between marital status and education level? In other words, are the proportions of married people different for various levels of education? For example, are college-educated people more or less likely to be married than high school educated people? So to answer those types of questions, we're going to go through a series of problems. And first, we're going to start off with conditional probabilities. So these are probabilities where we focus on just one group and imagine taking a random sample from that group alone. So in the last two sections, 5.1 and 5.2, every time we took a probability, we were taking it out of the total. But now we're just going to focus on a certain group. So that's called a conditional probability. So example, probability a person is married given that the person is college educated. So in this particular example, we're focusing not on all of these people, but only the group of college educated people. Another example, find the probability a person is single given that the person's highest education level is high school. So here it says given that, and now we're only focusing on the group of people who has the highest education level of high school. So what's the difference between a given that problem versus an and problem, which we did last section? Well, the first one says probability married and college educated. That one would use, this is the word and, right? That one would use the number in the intersection of married and college. So that's these group of people that are right here in this green area. Versus probability a person is married given that they are college educated. This would focus solely on the number of college educated and count that number in that group. So in this given that problem, we're just taking only the group of college people and we're focusing on the married people there. Right? We're not focusing on everybody because we're not even looking at the people who are in this blue married group here. Okay, so here's example 1. This is a review from last section of utilizing and in a probability. So let's go ahead and find the probability of a person being married and being college educated. So recall from last time, you're going to look for the people who are married and college educated. So that's this group of people right here. And we're going to take it out of the total because that's all the possible outcomes. So we're going to go 98 over 665, and that gives us 0.147 or 14.7%. Okay, so for example 2, given that, remember we're going to focus only on a certain group, not everybody. So questions asking, find the probability a person is married given that she or he is college educated. So we're only going to focus on the college educated group for our total and from this group. So find the number who, from this group, find the number who are married. So we're looking at the college educated group, which is here. And then from that group, we're going to look at only the people who are married. So probability that a person is married, given that he or she is college educated, would be 98, because, right, that's the event we're talking about. out of now only the college-educated people, which is 143. This gives us 0.685 or 68.5%. So the notation for writing conditional probabilities looks like this. Probably married given college educated. So it kind of looks like it's like a fraction, but it's not. This little vertical bar right here is indicating given that. So this is probability the person is married given they are college educated. So this bright part right here is the group that you're taking it from. So in general, probability of A given B means find the probability that event A occurs given that event B has occurred. So when calculating conditional probabilities, you can calculate it from tables by isolating the group when you're in a table, like how we just did in that example. But you can also calculate it by using a formula. So to find the probability of A given B, you would find the probability of A and B in the numerator and then divide it by the probability of B. Why the probability of B? Because this is the group you're taking it out of, right? So that matches. Okay, so we're going to do this calculation both ways. This first one is from the table, so we're going to isolate the sampling group. So we're asked to find the probability a person is married given that they have less than a high school education. So remember, the group that we're taking this out of or focusing on is the people that have less than a high school education. So of those people with less than a high school education, of all these people, now we're going to focus in on which or how many people were married from that group. So there's that 70 right there. So now to compute, we're going to take that, which is the event, married given, I'll say less than high school. We're going to do 70 divided by the group that we're taking it out of, which is all the people who have less than a high school degree, which is 125. So this gives us 0.56 or 56%. Okay, so now we're going to calculate the same thing, but we're going to utilize the formula. Okay, so here's the formula. Now let's start in the numerator, and we're going to calculate here in this numerator probability of A and B. So basically the event A is married, event B is less than a high school degree. So what's the probability of someone being married and having less than a high school degree? So we're going to look for that in the table, married and less than a high school degree. So here's 70 right here, married and less than a high school. So if we were just looking at the numerator, right, we didn't have this denominator, to calculate that, we would go 70 over the total, 665. Okay, now let's go ahead and calculate the denominator. So the denominator is just the probability of B, which is getting less than a high school degree. So all the people with less than a high school degree is 125. And if we were just calculating that probability, we would take it over the total as well, 665. So right now we have a fraction within a fraction, right? So we would do this. Divide by, I'm going to change that big division or fraction bar sign to a division sign. So now we're working with this. Remember how to divide fractions, right? We're taking the first fraction. This becomes a multiplication problem, and we'll take the reciprocal. What happens when we take the reciprocal? Well, we end up canceling out the 665, and now we end up with our fraction of 70 over 125. So you could calculate this the same way as if you just focused on what we did previously, which would make it a lot simpler because I'm showing you all this calculation so you understand the formula, right? But do you have to go ahead and do that? No, you don't have to show me all this work. So the most simplest way to do it is figure out the A and B, the numerator. So married and less than high school, which is this 70, right? So take that 70 and now just take it out of what group we're focusing in on. The group we're focusing in on is all of the people with less than a high school degree. That's 125. See how we end up with the same exact answer, right? But this second way was much simpler. So again, with formulas, right, it's always not to let the formula trip you up. It's just so that we can utilize that formula to input anything and it'll work out, right? But if we just think through it, then it's a lot easier to understand rather than memorizing it. Okay, so now let's talk about independent events. Those are variables or events that are not associated. So no association, they're called independent events. Two events are independent if knowledge that one has happened tells you nothing about whether or not the other has happened. Sometimes it's quite simple when you're looking at the problem. So for example, let's say I flip a penny and I want to know the probability of getting a heads, right? And then I'm going to go and flip a nickel and I want the probability of that getting a heads. Does the probability of getting a nickel heads, is that dependent on the first penny that I flipped? No, it's not. Does it matter? It's no matter what, it's going to come out 50%, right? So they're not associated. They're totally independent. So in symbols, A and B are independent events if probability of A given B comes out equal to the probability of A. If these two come out equal, that shows that nothing is being affected. One is not affected by the other, right? The flip of the nickel is not affected by the flip of the penny. Okay, so here's example 4. We're talking about independent events. So suppose a card is drawn from a standard deck of playing cards. Are the events, the card is a club and the card is black, independent? So let's recall the formula from previously. So there is the formula to check independence, although I'm pretty sure you can, you know the answer by now, being that we're talking about a club for event A and event B being the card is black. Okay, so on this left side where it says probability of A given B, I'm just going to expand this because remember when we're finding given that, we're actually finding the probability of A and B over the probability of B, right? We're taking it out of that event B. That's the group we're going to focus on. Okay, so in this numerator, we're going to try to figure out what are all of the cards. So I'm working on this right here. What are all of the cards in the deck that is a club and is black? Well, all of the clubs are black and there are 13 of them in the deck. So that probability is going to be 13. I'll write it down here. And then we're taking it out of only the black cards. So the total of black cards is 26. And you could go through this formula, remember, like going through all of the steps, but this is kind of like the shortcut version that I talked about, making it a lot more simpler. So now let's go through and do the probability of A. So now we're trying to figure out what is the probability that the card is a club, because that's event A. Well, all of the clubs in the deck is 13 out of the total in the deck, which is 52. So as you can see, these two probabilities are not the same. Therefore, the probability or the events, the card is a club and the card is black, are not independent. Which you kind of figured out earlier, like obviously it's not independent because all of the clubs are black, right? So they are associated. But this is how you can check if sometimes it's not so obvious. Okay, so now let's kind of do the same thing, but now we're going to look at a table. Are the events, person is selected, has a high school education, and person selected is divorced. Are they independent? So unlike that previous one, this one's a little bit hard to tell. Is a person that has a high school education affecting or associated with someone who is divorced? I'm not sure. So this is when you're going to go to that formula to make sure. Okay, so here I wrote out the formula. Remember this formula right here is to check independence, and this one on the bottom is simply just the given that drawn out. So let's go ahead and do the left side, the given that. You know what, I don't have room down there, so I'm going to do it over here. I'm going to just make a line, and I'm going to do it on those two sides. So let's start off with the given that problem. So probability, person selected has a high school education, and the person is divorced. So where are all the people that have high school education and also divorced? So that's right here, 59. And we're taking that out of the people who are divorced. And those are 84 people. Okay, so now we're going to figure out probability of event A. And those are all of the people that have a high school education. So high school education, all of those people are 397 out of the total of 665. So this first probability gives us 0.702, and then the second one gives us 0.597. So because they're coming out unequal, that means one has some kind of effect on another. So therefore we say that it's not independent. It has an effect. Okay, so in a and quotes problem, if you know that your events are independent, if you can see that, then you can go ahead and use this multiplication rule. It's basically just multiplying the two probabilities together. So here's an example. So we're talking about gender of babies. Suppose 49% of babies born in the US are girls. This is what we know. A couple has 2 children. Find the probability that both are girls. So the probability that the first is a girl and then the second is a girl would be simply just finding first the probability that the first one is a girl. So that's 49%, right? Because that's the probability of all US born babies. And then the second is a girl is also 49%. So then you just multiply those two together, and then you'll come up with the probability that if a couple has 2 children, that they're both girls. And for this one, we could have gone straight to this multiplication rule, right? Because we know that this is independent. We know that whenever someone has a child, it's not dependent on what their first child was. Okay, here's example 7. According to a Wall Street Journal survey, 70% of consumers prefer to shop online rather than in person at their favorite retailer. Suppose 3 customers are randomly selected with replacement from the population of consumers. So first question is asking, what is the probability that all 3 prefer to shop online? Well, are these independent? We're talking about 3 different consumers, so yeah, they're independent. So first probability, we can just go ahead and use that multiplication rule, right? So first consumer, second consumer, third consumer. This gives us the probability that all 3 prefer to shop online, which comes out to 0.343. Okay, so second question. What's the probability that none prefer to shop online? Well, remember the rule of complements, right? If you prefer to shop online, that probability is 70%. What's the probability that you don't prefer to shop online? Well, that's going to be 30%. So all 3 of them would come out to be 0.027. Okay, so last question is, what is the probability that at least one prefers to shop online? So this one's a little bit more complicated, but the important part to note here is that you should realize that at least one is satisfied. That's what we're trying to find, and that's the complement of none is satisfied. So since it includes all the categories except for none of them, so this is what we're really trying to find. Okay, so with that being said, remember complements, you're just subtracting from 1. So now we're going to go 1 minus the probability of none preferring to shop online, which we previously found. So we'll subtract 1 minus 0.027. This gives us a probability of 0.973. So the probability that at least one prefers to shop online would be 0.973. Okay, so up until this point, we've been just talking about theoretical probabilities, right? Probabilities based on theories. We didn't actually conduct an experiment. So now in this section, we're going to talk about empirical probabilities, where we actually do an observation or an experiment to figure out the probabilities. So remember, empirical is based on real life events. So some examples would be a baseball player's batting average, or the percentage of times a bus arrives late. So when we can't find data, or when a situation is just too complex for us to find the empirical probability, we can sometimes simulate the situation to generate the data that we need. So there's basically 6 steps for carrying out a simulation, and we'll go through all of these 6 steps in the next example. Okay, so we're trying to simulate the probability of 3 heads when tossing a coin 3 times. So step number 1 is to identify the random action and the probability of a successful outcome. So random action is the outcome of a single coin toss, right? So the probability of just getting 1 head is 0.5. Next, we're going to determine how to simulate this random action. So for example, we might use technology, a computer, or we might use the random number table that we've used previously. So if we use a random number table, and we say let even digits equal tails, and let odd digits equal heads. Step 3 is then to determine the event you're interested in. This is event A we're interested in. We're talking about simulating getting 3 heads and 3 tosses. So now we're going to explain how you'll simulate the trial. So we're going to read off 3 digits from a row. Each digit represents a toss, right? Tails, heads. And then 5, we're going to carry out a trial. So then you would record whether or not the event of interest has occurred. So if 3 heads occur, you would say yes, otherwise no. And then lastly, you're going to repeat that trial many times, at least 100. This is like the most important thing. And count the number of times your event occurred. So use the data to find the empirical probability. So repeating it many times is super important because, right, if you do it one time, you just read the 3 first digits in a random number table, you may not get the heads, which is okay, but if you repeat it many times, you should get closer and closer to getting the actual theoretical probability, right? If you add up all of the times you get heads over the total amount of times, that should come out to the theoretical probability. So at least 100 times. And I know 100 sounds like a lot, but if you're using technology, you could do this super fast. Okay, so here is the random number table. Let's try to simulate this coin toss. So starting with line 1, 2, 1, 0. So that's tails, head, tails. No, we didn't get it. So now we'll go to the next one. Now we'll do the next 3 numbers, which is 3, 3, 3. Heads, heads, heads. Yes, we got it that time. Now we're going to do the next 3 numbers, 2, 5, 2. That's tails, heads, tails. No, we didn't get it. So this is what you would be doing. We did it 3 times. You're going to do this 100 times. And that right there is what's called the law of large numbers. So that's saying if an experiment with the random outcome is repeated a large number of times, about 100 at least, the empirical probability of an event is likely to be close to the true probability. The larger the number of repetitions, the closer together these probabilities are likely to be. So as we get into chapter 6 and 7, this law of large numbers is going to become more increasingly important over those 2 chapters. So make sure this is clear and you understand this.